that needs to be drawn and things like that. So these connections are logical connections that we talk about. So what needs to be set up is, of course, all the state variables like SF, SN, RN, or what not, right? There could be other state variables in these protocols. We also need to allocate space for buffers. And then we need to initialize and then say ready, set, go, right? So we're ready to start at the same time. So an example of this connection setup and teardown procedure for a bidirectional service is something like this, that we start in the closed state. Okay, so we start here, nothing, you know, there exists no connection. And then at one side, say at A, we get a connection open request. And then what is transmitted then is a request to B to say, okay, can we talk? And then B says, I got your message, right? I'm ready to talk to you. But then data needs to go in the other direction also. And then there comes a packet from the other side say, can we talk? And then we answer, yes, we can talk. So there's a two-way handshake here. So if I'm A and there's B, I say, can we talk? And the other person says, sure. And then a little bit later, can we talk? And I say, sure. And then we're synchronized. Okay? So it's like a two-way handshake like this. And then we're in the established state, and then we do our ARQ protocols until, you know, there is no more data or something like that. And then there is like I'm done, can we shut off? The other one says, sure. I'm done, can we stop? And then the other side says, sure. And then we're in the closed state. Okay. You know, and then one can be stuck in the middle and things like that, and then you need to time out and whatever, right? But this is the principle, at least, for the setup phase. Questions on this? No? Okay. Maximum window sizes. Here, when we talked about this in the ARQ protocols, I basically says this is the size, but never really motivated why that was the case. So let's look at that detail a little bit. So remember that sequence numbers are typically n-bit numbers, so they need to be recycled. So what we need to do is always to avoid confusion between different packets with the same sequence numbers, because sequence numbers are reused. So we should never be in a situation where the transmitter and receiver thinks that a packet with a certain sequence number or could think that these are actually two different packets with the same sequence numbers. That I should never show. So I'll show you the example. Maybe this will clear up then. So there is a maximum size of the transmit and receive windows. Windows like this. Okay. So for stop and wait, we know that the send and transmit windows have size 1 because that's the part of the protocol. So that's not very exciting. But let's look at for go back n. So if we have n-bit sequence numbers, we know that the size of the send window should be less than 2 to the power of m. We know that the receive window size is 1. That's part of the protocol. So if m is equal to 2, that means that s size needs to be less than 4, right? So suppose it's 3, which is, you know, 1, 2, 3. Then if we transmit packet 0, okay, so we start. We transmit packet 0, and then the receive window slides because it's received correctly. It sends an ACK, which is lost. Packet number 1 is transmitted. We slide the window. ACK number 2 is lost. We send packet number 2. Go over here. We slide the window, and then that ACK is also lost. Okay. So this procedure, by losing ACKs, means that the receive window have slided to the right as much as possible, while the send window have slided nothing yet. Right? So here they are sort of at the maximum level of unsynchronized. asynchronicity, I guess, right? So in the transmit window, we have 0, 1, 3, 0, 1, 2, while the receiver is looking for packet number 3. But it's looking for this packet, right? So when packet number 0 comes over the channel here, this is then discarded because that has already been delivered. Okay, so this works out as it should. Maybe it's more instructive to see when it doesn't work. So now if we increase the window size here to 4, so here we have S size equal to 4, which is not allowed. Okay, so this is not less than 4. 4 is not less than 4. Okay, so here's we've done something bad, and we see we keep on doing the same thing, and at the end we keep on losing all the acts. So at this point in time we have 0, 1, 2, and 3 outstanding packets in the transmit window here, and then we start to retransmit, and then we retransmit packet number 0. Okay, now the receiver is actually looking for packet number 0. The receiver would like to get a packet with sequence number 0, but he wants that packet, not this packet. Right? So here's a problem that the receiver is looking for packet number 0 and gets packet number 0, but it's not the right packet 0, it's the wrong packet 0. So to avoid that this confusion should happen, the send window needs to be smaller than 4 in this case. Was that reasonably clear? Okay. So we never want to be in a situation where the receiver gets a packet with the right sequence number, but it's the wrong packet, right? Because it's another packet 0, not the packet 0 that I was looking for. It's looking for this. Sorry, looking for this packet 0, but it gets this packet 0. Okay. For selected repeat. Here, m-bit numbers, we have 2 to the power of m minus 1. Okay, so it was a little bit poor here. So when m is equal to 2, it's 2 to the power of 2 minus 1, which is 2 to the 1, which is 2. So window size 2. And here we have, here is S size, R size equals 3. So this is the bad example, right? This is the good example. So if the good example sort of works, you can look through this. Let's see what happens when we have a bad example. So the same pattern here is we transmit packets, we lose the acts, which means that we fill up the transmit window. And when there is a timeout, we transmit packet number 0. Okay, so we transmit this packet 0, while the receiver is looking for this packet 0, which is this packet. Maybe I should use another color here. So the receiver is looking for this packet 0, which is this packet 0, not that packet 0. Right. Same problem here, that we get confusion between the numbering of the packets and the actual packets. Questions? Okay, so this is a little bit of bookkeeping. Flow control. What is that? That's something which is in the data link layer typically, and it could also be in the transport layer in different parts. So flow control, what is that? It's used to avoid that a fast transmitter overwhelms a slow receiver. So if you have a device which is not capable of handling too many bits per second, you cannot simply blast it with gigabits per second, because then buffers would overflow and so forth. So how do we control that? Well, one way to do that is to use special control frames by the receiver to instruct the transmitter to pause, to wait, and resume transmission. And these could be called X off, means transmission off. So if I'm the receiver, I'm getting low on buffer space, I can tell the transmitter, transmit off, and then the transmitter will stop. And when I cleared up my buffer, I can send a transmit on message to the receiver. Transmitter, sorry. We can also do that by adjusting the window sizes at the transmitter side. So this is basically all I'm going to tell you about flow control. You can read a little bit more about this in the book, but it's not really rocket science. So I will just skip it. It's part of the course, but we won't spend much time on that in the lecture. Another thing which is not rocket science is framing and stuffing. So framing is the process of inserting special byte or bit patterns in a stream of bits to indicate the borders between adjacent frames. So what is a frame? Well, typically we have the header, we have some payload, and then a trailer, right? And then there is another header, payload, trailer. But at the receiver, if you just get a stream of bits, how do you know when a frame starts and ends? That's why one could put in these special bit patterns called flags, okay, to indicate the border between consecutive frames, because the next frame might come here with a header, then some data, say, and then another header like this, and then another flag and so forth, right? Okay, so in byte stuffing, we transmit bytes to start with. So the smallest unit we transmit is bytes. So there is a variable number of bytes here. So the flag is then a special 8-bit pattern, a special byte to indicate the beginning and end of a frame. It doesn't matter what it is. It's something that we just decided that this one we will use as a flag. Then what we need to do then is to do byte stuffing, and that is to put in a special escape byte in front of any flags that might show up in here, because maybe this byte is exactly a flag byte. Okay, so we need to somehow avoid confusion that this is actually a payload byte, not a delimiter between frames. So what we do then is that we put an escape byte in front of the flag byte. And when the receiver reads this, it sees, okay, here's the beginning, here's a header, blah, blah, blah. Escape flag. It means, okay, so this flag is not really a flag because there's an escape in front of it. So let's not ignore that flag until we find the final flag at the end. Okay, so byte stuffing is to put in escape bytes in front of any flag, and also in front of any escape bytes. We need that in order for this to work. And then at the receiver, we do byte destuffing. So we scan the payload from the beginning and replace any 2 byte patterns, which is escape X, where X is any byte, with simply X. Okay. So, for instance, if it's something like this, we have a payload and it happens to have a flag in it, a flag byte and an escape byte. These needs to be stuffed before we transmit. So what we actually transmit is a flag, header, byte, and then an escape in front of that flag, and an escape in front of that escape. Okay, so, and then the receiver gets this, starts to scan here. Okay, flag, good, header. Now comes data, data, escape. So escape flag, that means let's just remove this and keep the flag. And then we keep on scanning like this. Another escape, 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 escape. Well, that simply means that we should lose the first escape. So that's the destuffing. I mean, we enter them here at the transmitter side, but at the receiver, we remove them before we actually deliver the payload. And by doing this, we see that we can support any number of flags and escapes in any possible order here. They will all be preserved by this byte stuffing thing. Okay, I'll do bit stuffing also. It's basically the same thing. It's just now it's not exactly the same thing, but instead we have bits. You can read up on this. It's not very difficult, right? Essentially, we have a bit pattern, which is the flag. And that bit pattern is not supposed to end up in the payload. If it ends up in the payload, we put in a 0 to make it not a flag anymore. and then we take out the zeros at the receiving end. That's called bit stuffing. So you can look at this slide, you figure it out in 5 minutes, I think. All right, so that's it for today. So see you on Thursday.